welcome to this problem walkthrough. Today, we'll be exploring the problem number 1239, maximum length of a concatenated string with unique characters. This is an exciting challenge that tests our ability to work with strings, recursion, and backtracking. Let's dive in and break it down step by step. The problem asks us to work with an array of strings, ARR, where each string consists of lowercase English letters. Our goal is to find the maximum possible length of a string that can be formed by concatenating a subsequence of the strings in ARR, such that every character in the resulting string is unique. The input consists of this array of strings, and the output is an integer representing the maximum length of such a valid concatenated string. Let's consider an example. If ARR is un, iq, ue, we can form the string unique by concatenating the strings un and iq. The length of unique is 4, and since all its characters are unique, the output is 4. In the first example, we saw that concatenating un and iq forms unique, which has a length of 4 and satisfies the uniqueness condition. Other combinations like ue, iq, or un either produce shorter strings or result in duplicate characters. Thus, the maximum length is 4. Now, in another example, if ARR is cha, ar, ict, ears, we can form the string chires by concatenating cha and airs. It has a length of 6 and all unique characters. Concatenations like char act or actors are invalid because they contain duplicate characters. Therefore, the output in this case is 6. In the third example, the input consists of a single string, ABCDFGHIJKLMNOPQRSTUVWXYZ. This string already contains all 26 unique lowercase English letters, so no concatenation is required. The maximum length of a valid concatenated string is simply the length of this single string, which is 26. Now, let's review the constraints for the problem. The array ARR can have between 1 and 16 strings, and each string can have a length between 1 and 26. All strings consist exclusively of lowercase English letters. These constraints ensure that the input is manageable and that we can explore all possible combinations efficiently. There are a few edge cases worth considering. If all strings in ARR are empty, this violates the constraints since each string must have at least one character. If all strings contain duplicate characters, such as AA, BB, then no valid concatenated string can be formed, and the maximum length would be 0. If the input contains a single string with all unique characters, for example, ABC, the result is simply the length of that string. For strings with overlapping characters, such as AB, BC, CD, only non-overlapping combinations contribute to the result. To solve this problem, we need to find the longest valid string formed from a subset of ARR while ensuring uniqueness. A backtracking or bit masking approach is well suited to efficiently explore these combinations within the given constraints. To begin solving this problem, we can consider the brute force approach, which is based on exhaustive search. The intuition here is straightforward. We generate all possible subsequences of the input array, then check which combinations can form concatenated strings where all characters are unique. For each valid combination, we calculate its length and keep track of the maximum. The steps involve generating all subsequences of the array, concatenating the strings in each subsequence, verifying that the resulting string has unique characters, and updating the maximum length accordingly. While this approach is conceptually simple and guarantees correctness, its major drawback is the exponential time complexity. Generating all subsequences alone takes O(2 to the power of n), and checking uniqueness for each combination requires O(L), where L is the length of the concatenated string. This makes the overall complexity O(2 to the power of n*L), which can quickly become infeasible for larger inputs. Although it's a simple method, the exponential runtime highlights the need for a more efficient approach. An optimized solution can be achieved using backtracking combined with bit masking. This approach avoids generating all subsequences by exploring only valid combinations and pruning invalid paths early. Bit masking further enhances efficiency by providing a quick way to check character uniqueness. The key observations for this approach include the use of a bit mask to represent the set of characters in a string, where each bit corresponds to a character. For example, the string ABC translates to a bit mask of 111 in binary. Combining two strings is valid if their bit masks do not overlap, which can be efficiently checked using a bitwise in operation. Additionally, pruning invalid combinations early helps reduce unnecessary computations. To implement this, we pre-process the input array to filter out strings with duplicate characters, such as AA. Then, using backtracking, we explore combinations by maintaining a current bitmask in length. For each string, we check if its bitmask is compatible with the current one. If so, we update the bitmask in length, then recursively explore further combinations. Throughout the recursion, we track the maximum length and return it as the result. This method balances pruning and bitmasking to achieve better efficiency. Analyzing the complexity of this backtracking approach, the time complexity remains 2 to the power of n, as we still explore subsets of the input array. However, the pruning process significantly reduces the number of recursive calls, making it much more efficient than brute force. The space complexity is n, which is primarily due to the recursion stack. This trade-off offers several advantages. It reduces the search space effectively and employs bitmasking for efficient uniqueness checks. On the downside, it requires an understanding of both recursion and bitmasking, which can be less intuitive for some. Alternatively, we can approach the problem using dynamic programming by iteratively building valid string combinations while maintaining bitmasks. In this method, we initialize a DP list with a base state representing an empty string. For each string in the input array, we compute its bitmask and skip strings with duplicate characters. For each state in the DP list, we check compatibility with the current string's bitmask. If compatible, we create a new state by combining their bitmasks and updating the length. This iterative approach avoids recursion but comes with its own trade-offs, such as potentially higher memory usage for large inputs. In terms of complexity, the dynamic programming approach has a time complexity of n*2 to the power of m, where n is the size of the input array and m is the number of unique characters, typically 26 for lowercase English letters. The space complexity is 2 to the power of m, which may be significant for larger inputs. While dynamic programming avoids recursion and can be easier to implement iteratively, it may still require a substantial amount of memory. After weighing all the options, we chose to proceed with the backtracking approach combined with bitmasking. This strategy strikes a balance between conceptual simplicity, efficiency, and practical implementation. Unlike the brute force method, it avoids the infeasibility of exponential runtime by leveraging pruning and bitmasking to reduce the search space. While dynamic programming offers an alternative, its memory requirements can become restrictive. By combining backtracking with bitmasking, we achieve an efficient and scalable solution that is well suited to the constraints of this problem. The problem we're solving involves finding the maximum length of a concatenated string that contains only unique characters. We're given a list of strings, ARR, where each string consists of lowercase English letters. Our task is to combine subsequences from this list to form valid strings, and among these, determine the maximum possible length of a string with all unique characters. For instance, if ARR is un, IQ, UE, we can form combinations like unique, eq, or unique. The longest valid string here is unique, with a length of 8. To approach this, we use backtracking to systematically explore all potential combinations. At each step, we decide whether to include a given string in our combination or skip it. By ensuring that the resulting string remains valid, meaning all characters are unique, we can continue building and evaluating longer combinations. This approach avoids the inefficiencies of generating all subsets explicitly, allowing us to target only those that meet the problem's criteria. Now, an essential part of the algorithm is to ensure the validity of the strings we're forming. This involves checking whether a string or its addition to an existing combination contains only unique characters. For example, the string ABC is valid because all characters are unique, whereas ABA is invalid due to the repeated A. Additionally, when combining strings, we check if the characters in the new string overlap with those in the current combination. For instance, appending ABC to D forms ABCDE, which is valid, but appending ABC to CDE results in ABD, which is invalid due to the repeated C. Throughout this process, we maintain a variable, max_length, to track the longest valid string we've encountered. Whenever we find a new valid combination, we update this maximum length. The recursion terminates once all strings in ARR have been processed, at which point we return the maximum length found. The backtracking approach is particularly effective here because it allows us to explore the solution space without explicitly generating all possible subsets. By validating the uniqueness of characters at each step, we ensure that we're only working with valid combinations, which significantly reduces unnecessary computation. The algorithm also employs a pruning technique. If a combination is found to be invalid, we immediately skip further exploration of that branch. To implement this, we use specific data structures. A set is ideal for quickly checking the uniqueness of characters, offering 1 average time complexity for insertions and lookups. Additionally, string concatenation is used to build combinations dynamically during the backtracking process. In terms of complexity, the time complexity is 2 to the power of n asterisk k, where n is the number of strings in ARR and k is the average length of the strings. This accounts for generating all subsets and verifying their uniqueness. The space complexity is n plus k, which includes the recursion stack and any auxiliary data structures like sets. To better understand the algorithm, let's walk through an example. Suppose the input is ARR equals un, IQ, UE. We start with an empty string. Including un gives us un, which is valid. Next, adding IQ forms unique, which is still valid. Adding UE to that results in unique, with a length of 8, which becomes our current maximum. From here, we backtrack by excluding UE to explore other possibilities, but unique remains valid with the same length of 8. We then explore other combinations like IQ or UE individually, but none exceed the maximum length of 8. The final result is 8. For edge cases, if the input is empty, we return 0 since no strings can be formed. If the list contains single character strings, the result will depend on whether the characters are unique. For example, if all characters are unique, the result is simply the size of the list. However, if all strings in ARR contain duplicate characters, like AA, BB, the result is 0 since no valid combinations can be formed. This Python solution employs backtracking to solve LeetCode problem number 1239, maximum length of a concatenated string with unique characters. The goal is to maximize the length of a concatenated string with unique characters by combining substrings from the input list ARR. ### explanation. We first define the has_unique_chars helper function, which checks whether a string has all unique characters using a set. If the length of the set matches the length of the string, it means all characters are unique. The backtrack function is the core of the solution. It takes two arguments, index, which represents the starting point for the current recursion, and current, the concatenated string formed so far. The variable max_length is maintained globally to track the maximum length of valid strings encountered during the recursion. Inside backtrack, we first check if the current string current has all unique characters using has_unique_chars. If it does, we update max_length to the maximum of its current value and the length of current. If current is invalid, i.e., it has duplicate characters, we terminate this branch of recursion early. Next, we iterate over the remaining strings in the array, starting from index. For each string, we recursively call backtrack with an updated index, i+1, and the concatenated string, current plus ARR, I. This ensures that we explore all possible combinations of the input list. The maxLength function initializes max_length to 0 and starts the backtracking process with an empty string and an initial index of 0. Finally, it returns the maximum length found. ### complexity. Time complexity. The algorithm has exponential complexity in the worst case, as it explores all subsets of the input list. Specifically, it is 2 to the power of n*k, where n is the length of ARR and k is the average length of strings in ARR. Space complexity. The space usage is n plus k, where n accounts for the recursion stack and k is the maximum length of the concatenated string. This solution is concise and effective for solving the problem within reasonable input limits. Brief explanation highlighting that this is the Java implementation with the same logic as Python. Mention key differences like type declarations, class structure, and Java-specific collections, 45 to 60 seconds. In this example, the input array is un, IQ, UE. We start by defining a helper function, has_unique_chars, s, which checks if a string has all unique characters. Then, we initialize max_length to 0 and begin the backtracking process with an empty string as the initial current value and index set to 0. In the first call to backtrack, 0, the function evaluates the empty string using has_unique_chars, which returns true since an empty string is trivially valid. The max_length remains at 0 because the length of the empty string is 0. Now, we loop through the array starting at index equals 0. Concatenating current with rr, 0, gives us current equals un, and we proceed with this updated string. Next, the recursive call backtrack, 1, un, is made. The helper function confirms that has_unique_chars, un, is true because all characters in un are unique. The max_length is updated to 2, which is the length of un. The loop now continues from index equals 1, where current is concatenated with rr, 1, resulting in current equals unique. At this point, backtrack, 2, unique, is called. The function checks that has_unique_chars, unique, returns true since all characters are unique. The max_length is updated to 4, the length of unique. The loop proceeds to index equals 2, where current is concatenated with rr, 2, creating current equals unique. The next recursive call, backtrack, 3, unique, finds that has_unique_chars, unique, returns false due to the duplicate u. The function doesn't update max_length and backtracks to explore other paths, such as combining un with ue. Ultimately, the longest valid unique string length for this input is 4. In this second example, the input array is cha, r, act, airs. As before, we start backtracking from index equals 0 with an empty string as the initial current. Exploring combinations, concatenating cha with her results in char, which is valid since all characters are unique, and its length is 4. However, attempting to concatenate char with act creates a string with duplicate a, making it invalid. Another valid combination is cha concatenated directly with airs, producing chars, which has all unique characters and a length of 6. After testing all possible combinations, the maximum length of a valid unique string is found to be 6. In this final example, the input array is bb. Using the same backtracking approach, we start with an empty string and explore possible combinations. The first string, aa, is immediately invalid because it contains duplicate characters. Similarly, the second string, bb, is also invalid due to duplicate b characters. Since neither string is valid and no valid concatenations can be formed, the maximum valid unique string length remains 0. This highlights how the algorithm handles cases where no valid combinations exist in the input array. In this problem, we need to analyze the time complexity of recursively exploring all possible concatenations of strings from the input array, ensuring that each concatenated string contains only unique characters. The time complexity is primarily influenced by the number of recursive calls and the work done during each call. The number of recursive calls is determined by the backtracking function, which generates all possible subsets of the input array. For an array of size n, there are 2 n subsets, as each string can either be included or excluded. Within each call, there are 2 main operations. First, concatenating the current string with a new string, which takes L, where L is the length of the resulting string. Second, checking if the concatenated string has unique characters, which involves constructing a set and comparing its size to the string's length. This also takes L. Together, these operations define the computational effort per call. When we consider the total time complexity, the algorithm explores all 2 n subsets and performs L work for each subset. If k represents the average length of the strings in the input array, the time complexity can be expressed as 2 to the power of n*k. This accounts for the subset generation combined with the string concatenation and uniqueness checks. Now, turning to space complexity, there are 3 contributors to consider. First, the recursive call stack. Since the recursion depth depends on the size of the input array, this uses n space. Second, temporary strings. As the algorithm generates new concatenated strings, the maximum possible length of such a string is the total length of all strings in the array, which we denote as s. This contributes s to the space complexity. Additionally, the uniqueness check performed by the has_unique_chars function uses a set to store characters of the string being checked. The space required for this set is proportional to the length of the string, contributing L space where L is the string's length. Combining all these factors, the total space complexity is the sum of the space for the recursion stack, the temporary strings, and the uniqueness check. This results in an overall space complexity of O, n plus s, where n is the size of the input array and s is the total length of all strings in the array. To better understand the efficiency of the backtracking approach, let's compare it to a brute force method. A brute force solution would generate all possible concatenations of strings in the array and check each one for unique characters. This would result in a time complexity of O, 2 to the power of n times m times k, where m is the number of concatenated strings generated and k is the average string length. In contrast, backtracking significantly reduces unnecessary computations by pruning invalid combinations early. While the worst-case time complexity of backtracking remains O, 2 to the power of n asterisk k, this pruning allows the algorithm to avoid exploring subsets that violate the uniqueness constraint, making it more efficient in practice. Finally, let's analyze the algorithm's behavior in different scenarios. In the best case, where all strings contain duplicate characters, most branches are pruned early, leading to relatively fewer recursive calls and a time complexity closer to O, n asterisk k. In the average case, for a random set of strings, the algorithm explores a subset of the recursion tree, with time complexity approaching O, 2 to the power of n asterisk k. In the worst case, if all strings contain unique characters and all subsets are valid, the algorithm explores every branch of the recursion tree, resulting in O, 2 to the power of n asterisk k, time complexity. The space complexity remains O, n plus s, in all cases, as it depends on the recursion stack and the temporary strings generated. This analysis aligns with the exponential growth in subsets, alongside the linear work done for string operations, validating our earlier complexity calculations. When working on this problem, there are a few common mistakes to watch out for. First, not checking for unique characters in substrings can lead to incorrect solutions. This happens when we assume that concatenating any subsequence will naturally yield unique characters, which isn't always true. For instance, if you combine ABC and CDE, the overlapping C invalidates the solution. The fix here is to use a set or a frequency array to ensure character uniqueness. Another common issue is inefficient subsequence generation. If you generate all possible subsequences without pruning invalid ones early, you'll end up performing unnecessary computations, which becomes a problem for larger inputs, like arrays with sizes around 10,000. To address this, using backtracking or dynamic programming can help you avoid dealing with invalid subsequences. Lastly, don't ignore edge cases. Scenarios like an empty array, single-element arrays, or arrays where all characters are duplicates can cause incorrect outputs or runtime errors. Always test for these edge cases to make your solution robust. Now, another mistake to be aware of is overlooking time complexity. It's easy to assume your brute force solution will run efficiently without analyzing its actual performance. However, brute force often leads to exponential growth, with a complexity of O, 2 to the power of n, making it impractical for large inputs. The solution here is to analyze and optimize your approach to ensure it fits within the problem's constraints. Additionally, incorrect state management in backtracking is a frequent pitfall. If you forget to reset or undo changes during backtracking, it can result in incorrect outcomes because invalid states might persist into subsequent recursive calls. To fix this, always ensure that you revert all changes after each recursive call so that your backtracking process is clean and reliable. In a coding interview, there are some key insights that can help you stand out when solving this problem. Pay close attention to the input size and constraints, as these often provide hints about whether a brute force solution is feasible or if an optimized approach is necessary. It's also important to communicate the trade-offs between different strategies, like brute force, backtracking, and dynamic programming. This shows your ability to evaluate multiple approaches critically. Recognizing patterns is another valuable skill. Problems involving unique characters, subsequences, or concatenations often benefit from techniques like using sets, bitmasks, or recursion. Additionally, discussing edge cases with your interviewer is a great way to demonstrate thoroughness and a proactive mindset. Finally, when working through your solution, start with a brute force approach and then refine it. This iterative problem-solving process highlights your ability to optimize and improve your code over time. This problem also shares similarities with a few related problems that you might encounter. For instance, LeetCode 1239, which is this very problem, focuses on maximizing the length of valid concatenations.
Then there's LeetCode 46, which involves generating all permutations.
While the goals differ, both problems rely on exploring different combinations, making them conceptually similar. LeetCode 78, another classic problem, asks you to generate all possible subsets of an array, which again overlaps with the idea of working through subsequences. Finally, LeetCode 90 is a variation of the subsets problem but handles unique subsets, which ties closely to the challenge of managing duplicates in concatenation problems. Exploring these related problems can deepen your understanding of techniques like backtracking, recursion, and pruning invalid solutions. To wrap up, let's look at some alternative approaches and weigh their trade-offs. The brute force approach is often the simplest to implement, making it a good choice for small inputs. However, it becomes inefficient for large inputs because of its exponential time complexity, 2 to the power of n.
Backtracking is a more refined approach, allowing you to prune invalid solutions early and avoid unnecessary computations.
While it's more efficient, it can be tricky to implement due to the need for careful state management.
Dynamic programming is another powerful technique, optimized for larger inputs since it stores intermediate results to prevent redundant calculations.
However, designing the state transitions can be challenging and may require a deeper understanding of the problem. Lastly, bit masking is particularly efficient for problems involving binary states, such as ensuring uniqueness of characters. While it's a compact and fast solution, it can be less intuitive and harder to debug, especially for beginners. Each approach has its strengths and weaknesses, so choose the one that best fits the constraints and requirements of the problem at hand.
Great job following along.
To wrap up, we reviewed the solution to problem number 1239, highlighting the use of recursion and backtracking to manage constraints. Keep practicing problems like this to strengthen your problem-solving skills.
Thanks for watching, and see you in the next session. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!